Hey there, welcome back to the Enclosure Institute, where we talk about sealing enclosures and hopefully offer some helpful hints for enclosure designers. I happen to be Phil Taylor.
And I'm Jimmy Budd. Today we're going to talk about some common causes or conditions that lead to the failure of the gasket or seal. We're going to split the reasons why seals fail into two main categories. Those are failures related to materials and failures related due to design, geometry, or installation. While we're at it, we'll suggest a number of possible solutions to avoid these troubles.
As a reminder, we're primarily focused on gaskets and seals cut from sponge and foam materials. Almost all gaskets provide a good seal when the new device is fresh out of the box, but over time, many seals fail prematurely due to one or more stumbling blocks in the material or the design.
The first problem we'll discuss is applying too little or too much compression to the foam gasket. Incorrect compression, whether too little or too much, can lead to material degradation and a leak. Insufficient compression may leave gaps, while excessive compression can deform the material, reducing its effectiveness over time. As a guideline for a foam gasket, we recommend a compression range of 30 to 50% for optimal sealing performance. Of course, this can vary based on the specific material and your application requirements. Whenever possible, it's wise to conduct compression testing under the anticipated environmental conditions that your device will encounter. At Marian and Rogers, we can help by not only recommending the best material, but also the thickness and compression percentage for your device.
Perhaps the most common cause of gasket failures over time is stress relaxation due to compression set. Before we dig into this topic, there are several concepts that we need to make clear. The first of these is compression force deflection, or CFD. This is the force expressed in PSI or kPa that's required to compress a test specimen at a specific rate of compression to a given percent of its thickness. There are various ASTM and other test methods that prescribe the details of these tests, but in simple terms, CFD is the measure of the foam's resistance to compression. Or said another way, it tells you how soft a foam material is and how easy or difficult it is to compress.
Another property of foam we want to cover is density. Density of foam is expressed in pounds per cubic foot, or PCF, so it's simply a measure of weight. A common misconception is that to increase CFD, you must also increase density. This might be true only when comparing densities of the same foam type, but two different kinds of foams can vary greatly in both density and CFD. For example, Velara Type A, a cross-linked polyethylene foam, and 4 pounds per cubic foot density requires 10 psi for a 25% compression. Compare that to PORON in formulation 4701-30, a high-density urethane foam, which is 15 pounds per cubic foot density, more than 3 times heavier than the Velara, yet it only requires 3.1 psi for 25% compression, which is 3 times less than the 4-pound Velara.
Let's talk about compression set next. The compression set, or C-set value of a foam material is also determined by ASTM and other test methods. In these tests, a specimen is compressed to a given percentage of thickness and maintained in that compression over a prescribed amount of time at a given temperature. Some tests call for the specimen to be held in compression for a long period of time, like 24 or 72 hours. Others call for repeated compressions in the frequency and duration of each compression over a period of time. After the allotted time or the required number of repetitions, the specimen is released from the pressure and allowed to relax for another prescribed amount of time. Then its thickness is measured. The compression set percentage is the amount of thickness that is lost from the original thickness. For example, if a test specimen that was 1 inch thick before compression testing measures 3/4 of an inch afterward, then it is said to have a 25% compression set. The ability of a foam material to seal depends at least in part on the foam's elasticity. As the foam experiences compression set, the CFD of the foam is suffering. The foam is experiencing stress relaxation and a leak is likely to emerge.
How long it takes in days, weeks, or months for the foam to lose enough strength in your application so that it no longer provides an adequate seal is difficult to predict. But if such failure is critical to your device's performance, then a foam material with exceptional compression set resistance should be chosen. Materials with superior compression set resistance, such as PORON polyurethane or BISCO silicone, maintain their CFD and resist stress relaxation more than any other foam materials. These materials have compression set values of 5% or less, even in demanding environments. By comparison, neoprene and EPDM sponge materials have compression set values of up to 50% in some environments. At Marian, we demonstrate this property to our customers with our Test My Memory demo to show the excellent performance of BISCO and PORON compared to standard neoprene and PE foams. After comparing compression set after 24 hours, it's pretty obvious where PORON and BISCO excel.
The next problem that we'll discuss has to do with temperature. Problems occur when temperatures exceed the recommended limit for a material. Short spikes in high temperatures that are above a material's recommended limit may not cause immediate failure, but over time, high temperatures can cause seals to crack, harden, or lose elasticity, which then can lead to premature failure.
To avoid this problem, you should design with the worst case in mind. Although your device might be used in ambient conditions most of the time, if it will be subject to higher temperature in some cases, then you should design for those times. Material manufacturers should be able to supply upper temperature limits for both constant temperatures and intermittent spikes. As we've noted before, silicones like Rogers BISCO materials offer the highest heat resistance at 200 degrees Celsius, while neoprene sponge by comparison tops out at 121 degrees C.
Applications that involve abrasion, vibration, and repeated compressions can speed up a gasket failure simply because those conditions are hard on the gasket material. A static seal that's clamped and stable without movement doesn't experience the same stress as a dynamic seal. If the material chosen was a PVC foam, vinyl nitrile blend, or some neoprene and EPDM sponge materials, the physical abuse experienced in these dynamic applications will likely cause failure of the gasket earlier than expected. High-density urethane foam like PORON is more robust and durable and can extend the life of your gasket.
Now, let's talk about environmental factors like ultraviolet and ozone. UV causes elastomeric foams to age or decompose quicker. They'll harden, crack, and become brittle. As we discussed in the previous video where we reviewed various material choices, when it comes to resisting the ill effects of UV and sunlight, a neoprene sponge can be good, EPDM and high-density urethane are better, and silicones are the best.
Lastly, sometimes a seal will fail when it comes into contact with a chemical solution with which it's incompatible. In those cases, the foam may swell, start to decompose, and degrade. It gets gooey. The first solution to this problem is, of course, to plan ahead. Material manufacturers like Rogers can supply chemical compatibility charts that list many common industrial chemicals and their expected effect on their materials. These charts typically show compatibility as recommended or not recommended. But if chemical compatibility is a key concern, the best solution is to get specific. Tell us the specific chemicals, their concentration, and the method of contact with the gasket material. We can supply explicit recommendations, samples, and even in some cases, test results or first-hand evaluations.
Alright, that's enough about gasket material selection. In our next video, we'll continue our discussion on why seals fail, but focus on the reasons related to design, geometry, and installation. We promise you won't want to miss this one. Over the years, we've seen some gasket designs with very problematic designs.
Yeah, you could say we've come to the rescue once or twice. Well, we'll see you soon. I'm Phil Taylor.
And I'm Jimmy Budd. Thanks for watching.